Imagine a world where a farmer can simply ask a computer to diagnose a crop disease, and the system replies with a treatment plan without needing a PhD in computer science. This is the promise of conversational multi-agent AI systems for plant phenotyping. We are seeing the emergence of tools like PhenoAssistant and Aleks, which use large language models to orchestrate specialized agents. These agents handle everything from planning experiments to analyzing plant health data. The goal is to lower technical barriers and democratize access to complex workflows. However, while the software architecture is impressive, the physical reality of running these systems in remote agricultural environments introduces significant challenges. The real bottleneck is not the intelligence of the AI, but the connection between the field and the cloud. Consider the architecture of PhenoAssistant. This system is designed to bridge the gap between complex automated phenotyping hardware and non-expert users. It decomposes tasks into specialized agents for planning, data analysis, and visualization. A user speaks to the system in natural language, and the AI breaks that request down into executable steps. It leverages a data-driven loop where agents autonomously generate hypotheses and execute experiments via robotic phenotyping platforms. This mirrors human scientific discovery workflows, but it relies heavily on continuous data exchange. When a user asks a question, the system must retrieve context, process the query, and then send commands back to the hardware. In a laboratory setting, this happens in milliseconds. In a remote field, the network connection is often unstable. Here is the thing about latency. Latency is the delay before a transfer of data begins following an instruction. In a conversational system, high latency kills the illusion of conversation. If a farmer asks a question and the system takes 30 seconds to respond, the interaction feels broken. For PhenoAssistant to work effectively, it needs to maintain a stateful conversation where context is retained. Every turn in the dialogue requires the system to remember previous interactions. If the connection drops, that context can be lost or corrupted. The system might lose track of which plant variety was discussed or which experimental condition was active. This is a critical failure mode for an automated phenotyping pipeline. If the feedback loop is interrupted, the robot might stop working, or worse, it might execute a command based on outdated information. Now consider Aleks, which represents a step further toward autonomous scientific discovery. Aleks utilizes retrieval augmented generation and domain knowledge to iteratively design experiments and refine models without human intervention. This is a much heavier computational load. Retrieval augmented generation means the system is constantly searching through vast databases of scientific literature and experimental data to inform its decisions. This requires significant bandwidth. Every time the system decides to design a new experiment, it needs to pull in large amounts of contextual data. In a centralized cloud pipeline, this is manageable because the servers are close to the data centers. But when you move this to a remote field, you are pushing gigabytes of data over potentially weak cellular or satellite links. The bandwidth bottleneck is even more critical for Aleks because of the visual data involved. Plant phenotyping often involves processing images of leaves, stems, and roots to detect disease or measure growth. These images are large files. If the system is uploading raw sensor data from the field to the cloud for analysis, the upload speed becomes the limiting factor. If the upload queue backs up, the agent cannot make decisions in real time. It creates a lag between sensing the environment and acting upon it. In a biological context, time is everything. A disease can spread rapidly, and a delay in detection caused by network congestion could mean the difference between saving a crop and losing it. The architecture assumes a level of connectivity that simply does not exist in many agricultural zones. This brings us to the fundamental architectural conflict between centralized cloud pipelines and edge computing in the field. A centralized cloud pipeline means all the heavy lifting is done on powerful servers far away. This allows for complex models and massive context windows, but it requires constant, high-speed internet. An edge computing approach would process data locally on the farm. This reduces latency because the decision happens right where the sensor is. However, local hardware is less powerful than a cloud server. You cannot run the largest large language models on a small device in a field without draining power or overheating, so the system faces a trade-off. Do you send the data to the cloud and wait for the answer, or do you process it locally and risk missing out on the full power of the model? The current research suggests a hybrid approach might be necessary. PhenoAssistant and Aleks both rely on frameworks like AutoGen and LangChain to orchestrate agents. These frameworks allow researchers to assign specific roles to different software components. You can have one agent that handles the internet connection and another that handles the data analysis. In a high-latency environment, the connection agent would need to queue requests intelligently. It would need to know which tasks are urgent and which can wait. For example, checking a live temperature reading is urgent, but uploading a full report of the day's growth metrics can wait until the connection stabilizes. This requires the system to be aware of its own network status and adapt its behavior accordingly. Future implications suggest a move toward fully autonomous AI scientists in plant science. These systems will manage the entire research lifecycle from literature review to physical plant manipulation. To make this viable, the infrastructure must evolve. We need to see more robust edge computing capabilities that can handle the local processing of large language models. We also need better compression techniques for the visual data being transmitted. If the system can send a compressed summary of a plant image rather than the full file, it saves bandwidth. The explainability of decision-making must also remain robust across varying experimental conditions. If the network is slow, the system needs to be able to explain why it is waiting, so the human operator knows the system is still working and not just broken. Thanks for watching all the way to the end. I am a one-person team working hard to make each video better than the last. Subscribe if you found value. It is the best way to show support. Drop a comment with your biggest takeaway. See you in the next video.